Hello everyone, my name is ATIKAH binti SHAMSUDIN. My matrix number is AA21203, representing group 36. Before I begin, I would like to introduce my group members, Muhammad Farhan ISKANDAR bin ZAMRI, ARYSHA binti RIZMAN, and SITI NURDAMIA binti SHAHRUL HAIZAL. Today I will be presenting our finite state machines FSM design process. I will walk you through three main theoretical parts of our project: the state diagram, the excitation table, and the K-maps. Let's start with the state diagram. Our objective was to design a more machine FSM with a custom coding sequence. The sequence assigned to our group is 0, 1, 3, 2, 6, 7, 5, 4, and then it's looped back to 0. Since the highest decimal number in this sequence is 7, a 3-bit binary representation is required. We assign variables A, B, and C, and to present our 3 flip-flops, where A represent the most significant bit MSB and C represent the least significant bit LSB. Next, to make the sequence functional, a present state and next state transition table was constructed. To determine how the flip-flop should transition from one state to the next, I refer to the standard JK excitation table. By mapping the present states to their required next states, the specific J and K input values, such as 0, 1, and don't care condition, were extracted for every step of the sequence. Next, we move on to the K-maps. With the transition data fully mapped out, the next step is to find the simplest Boolean logic expression for the circuit. Here, the K-maps that were plotted for each flip-flop's input by grouping the ones and the don't care conditions. The simplified logic equation obtained are: for flip-flop A, JA equals to BC and KA equals to B bar C bar. For flip-flop B, JB equals to C and KB equals to AC. For flip-flop C, JC equals to A B bar plus AB and KC equals to A bar B bar plus AB. These equations serve as the theoretical foundation required to build the actual SFM logic circuit.
This slide shows the schematic diagram for our project, which is a synchronous sequential circuit utilizing 3 JK flip-flop. It is a synchronous design because all 3 flip-flops share a single unified clock source via the common clock line shown in blue at the bottom. On the right, we have our 3 main outputs, state A, B, and C. The transition of the states is controlled by the combinational logic gates in the middle, which act as the next state logic. For instance, the J and K inputs for flip-flop A are driven by NAND gate, while flip-flop B and C are driven by combination of AND and OR gates. When a clock pulse occurs, all flip-flops change states simultaneously to follow our design counting sequence. Thank you.
Hi and hello to my lecturer. Today I am going to present my finite state machine project, which is a more machine synchronous counter simulated using ATIKAH. The objective of this project is to design a custom 3-bit counting sequence using 3 JK flip-flops. For this circuit, the output transition through a specific sequence and displays it via 3 red LEDs representing bits QA, QB, and QC. Let's take a look at the core components of the hardware layout. To build this system, I have systematically arranged 5 integrated circuits on the breadboard. First, we have 2 74HC73 ICs, which house our 3 JK flip-flops. Next is the 74HC04 hex inverter to generate the inverted outputs QA bar, QB bar, and QC bar, followed by the 7HC32 quad OR gate, and finally the 7HC08 quad AND gate to handle our combinational logic execution. For the board infrastructure, the VCC and ground lines are tightly routed across all chips to ensure structural stability. The system is driven by a shared function generator, providing a square wave clock signal synchronously to all flip-flops, while the clear pins are tied to VCC to bypass the reset during operation. The behavior of the FSM is determined by state excitation equations derived by the state transition diagram. I have carefully wired the combinational feedback path as follows. For flip-flop A, the input JA is driven by QB.QC using the AND gate, while KA is fed by QB bar, QC bar. For flip-flop B, the input JB receive QA bar dot QC and KB receive QA dot QC. For flip-flop C, the input JC use the OR gate to process QA plus QB bar, while KC is directly linked to QB without needing any logic gate. All these logical loops successfully feed back into the memory elements to regulate the state progression cleanly. As you can see, the power supply reads a stable and safe active current, meaning there are no short circuits or floating states.
Hi, Assalamualaikum. My name is SITI NURDAMIA HAIZAL. My metric number is AA250102. Today, I will present a simulation of a parallel and shift register using the 7476 JK flip-flop. I will begin the simulation based on table 1. For line number 1, when all inputs are set to 1 and the clear input is also 1, all outputs remain 0. For line number 2, all inputs are set to 1 except the clear input, which is 0. The outputs remain 0. For line number 3, when the clear input is 1 and only input B is 0, the output shows that only B is 1. For line number 4, when the clear input is 1, all inputs are 1 and a clock pulse is applied once, only output C becomes 1. For line number 5, after applying another clock pulse, only output D remains 1. Next, after applying a third clock pulse, only output A becomes 1. Then, after applying a fourth clock pulse, only output B remains 1. Finally, after applying a fifth clock pulse, only output C becomes 1, while all outputs remains 0.
My name is ARYSHA BINTI RIZMAN. My metric number is AA21203. For line number 9, all inputs are set to 1, while the clear input is 0. For line number 10, inputs A and D are set to 1, and the clear input is also set to 1. For line number 11, all inputs and the clear input are set to 1. After applying one clock pulse, only outputs C and D became 1. For line number 12, the same procedure is repeated, and the outputs remain the same, with only A and D equal to 1. For line number 13, all inputs and the clear inputs are set to 1, and after applying the one clock pulse, outputs A and B become 1. For line number 14, the same procedure is repeated with another clock pulse, and the outputs remain B and C equal to 1. Finally, for line number 15, all inputs and clear input are set to 1, and after applying one clock pulse, outputs C and D become 1.